Hridaya, can you see the screen?
Yes, ma'am.
So let's begin, Hridaya, now. So today the ether ka preparation we are done, properties will be started. Already I think we have started, right? Preparation we are done. Did we start properties? Anything? Did I discuss with you? Nothing, right?
No, ma'am.
Today we have to. Okay. So Williamson synthesis preparation we have done. I can see till here we are done. Let's start the physical properties today. Physical properties of ethers. So same thing, boiling points and solubility we do over here. So ethers have less boiling point than alcohols. Okay. Why is that so? Because ether ka look here the structure ROR dash. Okay. So here we can say the oxygen atom is bonded with the two terminal carbon, isn't it? If I write the example, I would write CH3 over here, CH3 over here. Means oxygen is not having a free bond formation with the any other compound, right? Or itself cannot form intermolecular hydrogen bonding. So what we are observing in the ether, it's absence of hydrogen bonding, right? Due to which we can say this compound will be having the constituents will be the present between them, or the bond present between them, or how are they held? They are held with the weak, we can say the interaction or with the intermolecular force of attraction, right, between them, since there is no hydrogen bonding present. So we can say over the reason why ethers have a so, or it has a less boiling point than alcohol. The reason is due to absence of hydrogen bonding. So we do not get hydrogen bonding over here. This is the most important thing we can have over here. Hydrogen bonding is absent. And when we are showing the solubility also, this compound is, we can say, miscible in water. So what happens in the miscibility characteristic? Now, when it comes over here, this part, hydrogen can come and attack, but itself, ether molecule I'm talking, they cannot form hydrogen bonding, right? So miscibility ke case mein, we can say the possibility is there, we can have hydrogen bonding with water. But when we are talking about the boiling point, ether molecule itself cannot held with the intermolecular hydrogen bonding. There is a lack of hydrogen bonding. Okay, so remember, this is very important. Ethers are miscible in water. It can be understood by drawing the structure of the hydrogen bonding with water. Miscible in water. So what is the reason? We say this is due to the formation of hydrogen bonding with water. Clear, Hridaya?
Yes, ma'am.
So let's see over here the hydrogen bonding structure, then it will be more clear to you. Oxygen and two sides I'm taking alkyl group. This is the ether part I have taken, and water molecule I'm taking over here. Okay. So this all angle or this we can say distribution goes in this case. So here we can say the hydrogen bonding will be present now between ether and water molecule. Okay. And water molecule itself will be having a covalent bond. Further, it can be possibility, right? I did not make over here, so further ke liye I can reduce the size of the water and can go further. Again, you could see there is a ether molecule. So this is your ether molecule, right? And this is your water molecule, and this is intermolecular hydrogen bonding. Clear?
Yes,
So
ma'am.
even though this part has the same ether and connected with intermolecular hydrogen bonding. Are you clear, Hridaya? So it is very much clear among like ether, or we can say ether cannot form intermolecular interhydrogen bonding. That's the reason they are showing less boiling point than alcohols. So Hridaya, if I'm talking in alcohol case, so we have seen that like we this chapter is actually alcohols, phenols, and ethers. So we have seen the boiling point of phenol is higher than alcohols, and alcohols are having boiling point higher than ethers, isn't it? And ether here, if we compare now, the order goes phenol first, and then will be the alcohols, and then will be ethers. So all these characteristics are now we can say have a same explanation. The reason is hydrogen bonding over here. So due to hydrogen bonding, we can say this is actually the order of the boiling point, decreasing order, I would say, decreasing order of boiling points. Clear, Shradya? So phenols are more having boiling point, and we can say the intermolecular hydrogen bonding, which generates among them, it's more than alcohol and then ethers. Ether does not have among itself. Okay, miscibility or solubility, I can say the reason we have over here, it is soluble because it is able to form a intermolecular hydrogen bonding with water molecule. That is why we are seeing the solubility over here. No phone over here. I don't have phone. Go. So here now we'll go for the properties. Yes. No, baby. So let us start the chemical properties after physical properties. So let me conclude the physical properties once again. In physical properties, we have learned about the boiling points, and second, we have learned about the solubility, that is also called the miscibility. So we say the ethers are having the less boiling point than the alcohols and phenols because they do not have intermolecular hydrogen bonding. And second, ethers are soluble in water. Why? Because they are able to form intermolecular hydrogen bonding with water. Are you clear, Hridaya? So this is the overall. Let's start the chemical properties. So in chemical properties, they are the first thing I would say how it is getting prepared. Preparation we are done by the Williamson synthesis. Did you remember the Williamson synthesis? How do we prepare? We take the sodium salt, sodium alkoxide, and treat with the haloalkane, right? So this ether, it means somewhere related with the haloalkane, isn't it? So we can same way we can even produce haloalkane from ether. If ether reacts with acid, like acid halide specifically, not sulfuric and nitric acid. Acid halide ka meaning is that should have halogen atom along with it, and along with the hydrogen. Acid means they should contain hydrogen compulsory. And when I'm talking about halide, so it must hold the group 17 element, either Cl or fluorine or bromine or iodine. So combination can go HCl, right? HF, HCl, HBr. I meant to say that this is acid halide. Are you clear?
Yes, ma'am.
Okay. So acid halide can form halo, we can say alkane, when it is treated with the ether. So ether property is ethers on heating, we can heat the ether with the limited quantity of the hydrogen halide, so we can have the mixture of alcohols and alkyl halide. Okay, so basically it's like a reversible looks like, but the thing over here, we do not get sodium salt, because we do not take that compound related over here. That's the reason. So what is the product formed over here as alcohol and haloalkane? Clear? So it's a looking like a little Williamson synthesis ka vice versa, right? So first property, as I said, what I'm doing is ether heated with acid halide. Acid halide, generally it can be represented X. X means FClBr. Let me, for your reference, I would write over here, it's a group 17 element. X means F, fluorine, chlorine, bromine, and iodine. Clear? So how will it react? Look at over here. I'm taking the general reaction ROR dash. This reacts with the HX, right? So what do you get over here? Let me write this way, okay? H and X. So I would say this R and X is produced, right? What is Rx called as? Let me not specify the X dash, let it be common. R and X, it is formed. So we get as the product, H goes over here, isn't it? So what do you get as the product? ROH and RX. Is this clear? It's alcohol and we get haloalkane. Clear?
Yes, ma'am.
So exactly like a vice versa, you can say only the thing Williamson synthesis may we take the sodium alkoxide, here we are taking ether and haloalkane, right? Sorry, acid halide. So we are getting alcohol and haloalkane. So I would write one example, Hridaya, complete this. It's a diethyl ether, C2H5, both the sides we have, and treated with the hydrogen iodide. You know what is hydrogen iodide? I told you, acid halide. So now the product forms over here, Hridaya.
C2H5OH
Very good.
plus C2H5I.
Yeah, well done. So this is iodoethyl, or we can say ethyl iodide, or iodoethane, anything you can call it, ethyl alcohol, iodoethane, or ethyl iodide. So we get the ethyl alcohol as the product, and we get ethyl iodide. IUPAC name will be iodoethane from the diethyl ether. Is this clear, Hridaya?
Yes, ma'am.
Okay. Now, how will it react with the aryl ether? The same acid halide, how it reacts. So let's see with aryl ethers. Okay. So second one, acid halide reaction with, or aryl ether reaction with, any sentence you can write. And aryl ethers heated with acid halide. Let's see what happens. Okay. So look at over here. We have the compound aromatic and O, and here alkyl. So this is an example of aryl ether. Okay, this is an example of aromatic ring we have, and the O and R we have alkyl. So it is treated with the HX same way. We get the over here product as phenol. Even ether can produce phenol and gives the halo alkane. Easy. So example we'll see. If I take suppose R is equal to CS3, then the compound will be called as anisole. It is called as anisole. So anisole can be treated with hydrogen iodide. Tell the product, Hridaya.
Right. And OH.
Phenol, yes, same as well. And
CH3I.
exactly, methyl iodide we get as the product. Well done. Okay, so Hridaya, we are done with the acid halide reaction. Now we can go for the next reaction, which is all the electrophilic substitution for the aryl ether we have to study over here. So aryl ether ke saath we have the reaction. We do not have with the aliphatic. Okay, aliphatic ka only one reaction you have, and one is the reasoning question we have. We'll do after doing the all electrophilic substitution reaction. Okay. So basically, anisole is example taken. This is the compound which you have to study as a chemical property of aryl ether. This is as taken in your textbook syllabus. Only this compound ka property you have to study. It means this compound will be showing the electrophilic substitution with bromine, with nitric, with Prudhoe-Kraft alkylation, all such reactions. So we will be learning all this that reactions and for this compound. So let's see anisole. So now chemical electrophilic substitution, as I said, will start the first one. Anisole reacts with bromine. Okay. Anisole reacts with bromine. So bromine in ethanoic acid. Bromine in ethanoic acid. So we are seeing bromine, it is in ethanoic. It's not a bromine water. So obviously, like electrophilic substitution, may we get the two products. Remember, yesterday we have learned that would be para position and the ortho position. So bromine will be taken in ethanoic acid. Correct. So product forms over here as para and ortho. Just here, yeah, bromination when we are doing it will be ortho and the para derivative. This position is ortho, and the para position goes the opposite with respect to the methoxy. Correct. O CH3 and Br comes over here, right? So we call this compound as ortho bromo anisole. Is this clear? And this is called para bromo anisole. Is this clear?
Yes, ma'am.
This is bromination. The next we have the Friedel-Crafts acylation and alkylation of anisole, which is very important reaction. Friedel-Crafts ka reaction. Friedel-Crafts happens in the presence of two reagents. We can say if I'm talking about alkylation, then it will happen in the presence of alkyl halide. When I say about the acylation, it happens in the presence of acyl chloride. That's a difference. Got it? So basically, Friedel-Crafts shows two reactions. One is the alkylation and another is acylation. So alkylation happens in the presence of alkyl halide. This is the reagent, alkyl halide. Example of alkyl halide is CS3Cl. Okay. This happens in the presence of acyl chloride, or you can say acidic chloride. Okay. What is the example of this? CS3CO aa jayega. That's it. This is called acetyl chloride or acid chloride. Clear?
Yes, ma'am.
So let me write acetyl chloride over here. That would be better. Otherwise, there will be a confusion with acetic chloride and this. Okay. So examples are clear and the reaction would be clear. Let us do the first one. Friedel-Crafts alkylation, which I have written. Okay. So the first Friedel-Crafts alkylation will happen in the presence of this reagent. This is the reagent. The reactant is anisole. So we are doing the Friedel-Crafts alkylation of anisole. Anisole is the reactant. So we will take over here benzene OCH3 What is this called as? Anisole. And since we are taking the two products, so 2 moles have to be taken here. Okay. And similarly over here, and the 2 moles of the methyl chloride as well. And this happens in the presence of anhydrous aluminium chloride. This is actually your Lewis acid. Okay. So reaction takes place and the product as usual ortho and para derivative we get. So OCH3 with respect to this Cl will be taking H out from this corner. So HCl goes out, right? And CH3 gets up substituted over here. Similarly, para position se hydrogen takes the Cl, HCl goes out and CH3 comes over here. So we get the para product like this. Are you able to understand, Rudya?
Yes, ma'am.
So I'm now removing all such things. This is how reaction takes place. So we get ortho, we call it as a ortho. Now here this methyl and methoxy, which is higher given the preference. So we say this is together methyl with the benzene toluene it is called as. So we call it as a 2-methoxy toluene. What do you call this compound as? 2-methoxy toluene. This is clear. And this is called the 4-methoxy. With respect to this, as will go over here, 4th place. So OCH3 given the less preference, CH3 is given more. So along with the CH3 benzene cause toluene. So this is the major product, 4-methoxy toluene. Clear?
Yes, ma'am.
And here we can see the 2 moles of hydrochloric acid out. I showed how to remove. Yes?
Yes, ma'am.
Okay. So this is about your alkylation. Acylation में anisole will do. So anisole Friedel-Crafts alkylation, acylation of anisole, acylation when we do, this is suppose the anisole OCH3, ठीक है? So acyl के लिए acetyl chloride we will be taking. And same way, H will be removed, HCl goes out, and we get the COCH3 substituted over here. So it happens in the presence of anhydrous chloride, anhydrous aluminium chloride basically. And we get the loss of HCl over here. We get product as O, CH3, CO, and CH3 over here. Is this clear?
Yes, ma'am.
Okay. So very important to note over here, we get as the COCH3. CO is the carbonyl bond, carbon double bond, oxygen. Okay, so if you just take COCH3 with the benzene ring, it is called as acetophenone. What do you call this as? Acetophenone. So we say this is actually the methoxy. Now with respect to this is second place. We call it as a 2-methoxy acetophenone. And here what do you get as next product? OCH3, para place will come COCH3. So we call it as a 1, 2, 3 place, third place, and fourth place. We call it as a 4-methoxy, right? 4-methoxy acetophenone. Clear?
Yes, ma'am.
Okay. So now nitration of anisole. Nitration reagent is concentrated. HNO3 plus concentrated H2SO4. Remember, okay? Clear? So the nitration of any sol gives the mixture of the compound, which goes to it. It doesn't happen in the other case, like the phenol case, it gives the one product, single product. But here we get the substituted product. Okay. So what are the substituted product we get over here? Let me tell. Any sol, if we are treating it with the concentrated nitric acid in the presence of sulfuric acid, concentrated sulfuric acid will produce two product as usual, nitro derivative, nitro substituted orthoplase and a paraplase. So two nitro anisole as the minor product. The major always goes in electrophilic substitution is the para position. So OCH3 para position, opposite position is a para. So we can say the 4 nitro anisole. This is the major product. Clear? So overall, we are done with the what do you say? The properties over. The last which I said we will be doing. Before going to this, let me tell you, anisole undergo the electrophilic substitution reaction where are at ortho and the para. Okay. So if they ask, how will you explain it? Why it is going to ortho and so resonance structure. So that is very, very important. Resonance structure, we can take help and we can draw and show the diagram how the pi electron delocalized and these places are active. Okay.
Yes, ma'am.
So can we draw the resonance structure and see the negative ions are are appearing at ortho and para position? So let's see the anisole ka resonance. I would be taking some different colors. So it gives energy to us. So we'll take O and a pair of electron over here because oxygen bonded with the methyl, right? So this contains alternate position double covalent bond. Now we are shifting this lone pair towards this. Obviously this cleaves and goes to the corner carbon, right? Now the resonance symbol, double-headed arrow. Since the look, we can say electron displacement happened. Now the movement we can have double bond leads formation, and yahan pe we can have the negative ion formation because bond is shifted to corner carbon, being made it as a carbon ion. Since this oxygen has given its pair, so contains positive over here, right? Now what is this position? We call it as a ortho, isn't it? Now we'll move this and we'll move this. Hridaya, are you able to understand?
Yes, ma'am.
We got the ortho. The ticked one is ortho. Let's see over here. So we are taking with respect to this group 1, 2, 1, 2. This position is ortho position, right? Let's see over here. Now we shifted this bond over here, this negative charge generated, correct? Now we'll be shifting this over here and cleaving this part. So what do you see? This part is active now. What do you call this part? Para. So 1, 4 is what you call as para derivative. Para position. Clear?
Yes, ma'am.
Okay. The resonance structure next goes. Sorry. Negative charge generated, double bond, double bond, double bond over here, O positive and CH3. Hridaya, let me highlight this part. If you take with respect to this side, like also, this is 1, so this is 2. Like we are gone to anti-clockwise direction. So this is also what you call the ortho position only. What do you call this position as? Ortho position. Is this clear?
Yes, ma'am.
So where we are getting the negative charge appearing during this process, resonance structure at second place, at fourth place, And again, at the if we consider from the sixth place, means from the anti-clockwise direction, it will come to the second place. So we call this also as the ortho position. Either you can go for the clockwise direction or you can go for the anti-clockwise direction, right? So 1, 2 always will be the ortho, 1, 4 will be para, 1, 3 is meta. We are not getting third place by negative appearance, isn't it?
Yes,
Right?
ma'am.
So it means electrophilic substitution reaction पे we get the ortho and para derivative as the product. Whereas the para is stabilized. Para is more and major product. Higher percentage of the major product, mean can say para is produced. Clear? So this is the reason anisole undergo the electrophilic substitution and it produces ortho and para derivative. Right? I hope you are done with the properties now. Properties of the anisole completely. You do not have very much. You have only three major reaction. Let me just revise. Anisole ka reaction with the bromine you have. This is under the halogenation basically. Okay, this is the first one. Then second, you have alkylation, right? Friedel-Crafts reaction where we have acylation and alkylation. Alkylation happens in the presence of alkyl halide. Acylation happens in the presence of acetyl chloride. So we get the compound toluene and the acetophenone without methoxy substituted. Nitration happens in in this case, anisole gives ortho and para derivative. It is not like the phenol as gives a single product by using the concentrated nitric acid. Here we get the two products, ortho and para derivative. So why are we having ortho and para derivative major product as the para over here? So resonance structure helps us to study that. Resonance structure says that second place and fourth place the negative ion is appearing while doing the resonance structure. So we say that is most we can say active place for substitution. A group can go and substitute. That is the reason anisole gives electrophilic substitution at ortho and para. Clear?
Yes, ma'am.
Now we have the last reaction. As I said, it is a part of your aliphatic ether, I would say. I didn't do there because it is quite different from other properties. So let me see over here. If I take tertiary butyl, okay, tertiary butyl one side, and this is properties may only will come. So quite different than others. So CH3 and OCH3. Like first property, what you have seen, reaction with the acid halide. The same we are showing. Reaction with acid halide. Which reaction? Ethers reaction. Okay. So this is little quite, I can say, different. We have acid halide. We are taking concentrated HI. We are taking over here. So now the product, how we can say over here, this product I part will be going to the side where we have higher number of carbon. Means this part goes out, gets separated, and I goes to carbon because this is positive and this is negative. This generates negative, this generates positive. Similarly, this generates positive, this generates negative. So you can understand opposite charges will be attracted, right? So we get as the product over here as this. So this question is very important, Hridaya. That's why I took it in a separate and taught you this part. This may be given to complete the reaction. This question is very, very, very important. So you may be given this part and asked to complete the reaction. So you have to write the just product in examination. Very, very important. Okay, Hridaya?
Yes, ma'am.
So we are done, total completed this chapter today. We are ethers also done. I'll just take a 1 minute. So Hridaya, I will teach you now the summary part. As I promised you, I'm going to make this chapter very easy for you. So let's begin now. So here we go with the preparation and the properties ka flow chart. Okay. So reaction mainly because the concept can be can be read and can be okay, revised, but the reactions are like quite always we get confused by remembering reagent and all such reactions, isn't it?
Yes, ma'am.
So let's begin. Alcohols and phenols ka flow chart I will be teaching you. This is going to help you a lot. Remembering like product, reagent, okay, everything I would say. Very, very important. So you want to start from the backside or from the beginning? Alcohols to start kare. We'll start from alcohols.
Yes, ma'am.
Preparation and then properties will go.
Yes, ma'am.
Okay. So let's do the preparation of alcohols. So if we go for the aromatic ring, this basically because aliphatic ka to we have mechanism involved in that. So let's begin the preparation of alcohol flow chart. Okay, so let's see over here how it can be prepared from chlorobenzene. This is specifically phenol के लिए I would say the phenol के लिए preparation of alcohol. If I okay, alcohol also we can do, no problem. So if I'm taking the alcohols, so I would be taking first compound as R CH double bond CH2 alkene say, right? Alkene, and will be treating the H2O. This is actually called the acid reaction, correct? And produces as the compound alcohol, correct? So what do you get as the CS 2 degree alcohol? So we say alkene में unsaturated alkene. Unsaturated कैसे पढ़ेंगे? This is how. Okay, one carbon and we have unequal numbers. So this is unsaturated. ठीक है? Or you can say unsymmetrical. Unsymmetrical will be better. Clear? Unsymmetrical alkene. So alkene that gives out the 2 degree. Symmetrical will not. Unsymmetrical will give the 2 degree alcohol. And we can say this follows a rule. Let me highlight over here. It follows Marconi-Kaf's rule. Okay, and what is Marconi-Kaf's rule? The less number of hydrogen where we have, there we get the right. This produces the H plus and the OH minus. So where that H plus and OH minus will go to the carbon where we have less number of hydrogen. That is why it produces 2 degree alcohol. Is this clear?
Yes, ma'am.
Second reaction we have with the hydroboration, right?
So you can break.
Hydroboration. Hydroboration I taught you in a very multiple steps, right? I can take this in a single, that day I told you it can be done in a single as well, correct? The same thing I'm taking in a single way, single step. Let's learn this how to be BH3 na, so twice needed here. I'll increase the number of, because three hydrogens will be right, 3 moles will be taking. And here this follows because it happens over water and H2O2 peroxide we have. Because of this peroxide, we can say which rule will it follow. I'll write later. Let me complete this part. And it removes 3 OH minus. So what do you get as this alkene? This is unsymmetrical only. But by hydroboration, it produces 1 degree alcohol. Different, isn't it? So it produces 1 degree alcohol, propanol. So even it is helpful for propene, gives propanol conversion. Many questions can be solved. Okay, propanol. So how many moles do we get? 3 moles. The byproduct is boric acid. So that is OH whole thrice. H3BO3 also you can write. That would be better. H3BO3. Okay, this is what you call as boric acid. Okay, yeah. So as I said, it follows anti-Marconi-Kaf's rule. it follows anti-Marconi-Kav's rule. So anti-Marconi-Kav's mein this carbon gets the negative particle. Okay, that is only the thing. So BH will go to this carbon where you have higher number of hydrogen, and this is what 3 steps will be taken, and finally this will produce as the 1-degree alcohol. Got the difference? So hydroboration, say what do you get as the product? 1-degree alcohol. See, alkene is producing 1-degree alcohol when it follows anti-Marconi-Kav's rule. But what is this name of the reaction? Hydroboration. When it goes a simple reaction like hydration, what is the name of this reaction? What do you call this as? Hydration. Catalyzed, acid catalyzed. This is by the acid catalyzed, right? Hydration. By this, it will give the Marconi-Kav's rule and follow Marconi-Kav's and produces 2-degree alcohol, right? This is the difference we have. So making flowchart for alcohol, it is quite difficult because it has its separate properties, and it is not all together. If all are similar property, then we can make the flowchart in one. So here I'm highlighting the points. Do remember this? Unsymmetrical alkene following Marconi-Kav's rule. This is following anti-Marconi-Kav's rule. Unsymmetrical alkene, but gives the 1-degree alcohol. Clear?
Yes, ma'am.
Okay. Now the next property will be taken. Preparation can be taken in a flow chart. So I would write over here. From carbonyl compounds. Carbonyl compounds like aldehyde and the carboxylic acid. So these compounds, when they undergo the reaction like reduction and the oxidation, there will be a likewise vice versa reaction possible. So carbonyl compounds will be taken over here. If you remember, aldehyde gives 1 degree, ketone gives 2-degree alcohol. So we can use the aldehyde ke liye RCHO, right? This will be taken the nickel and the palladium in this presence, or can be taken lithium aluminium hydride as the reagent, right? So these compounds, they are treated with the lithium and aluminium. What they are acting as? Basically reducing agent. They are acting as reducing agent. So they remove oxygen, right? Carbonyl group mein they are giving 1 hydrogen and add up the 1 hydrogen. That's the reason they help in the reduction process. So we get the product as CHO converts into CH2OH. So we get product as CH2OH. This is 1 degree alcohol. Clear? Ketones
Yes, ma'am.
are C double bond R dash over here we can write. This reacts with the sodium borohydride NaBH4. This is also a reducing agent. What is this? This is also a reducing agent. This also gives a C double bond O goes into which conversion? CHOH. So this produces 2-degree alcohol. This is the difference. This produces 2-degree alcohol. Now how we can technically like seeing the bonds, and technically we can also correlate how it happens. Look at over here. So 3 sticks and the 4th stick needed with the oxygen. It means it has only option of the 1 stick. So hydrogen only can be attached. It means we have ketone say 2-degree alcohol ka production. Are you clear?
Yes.
Right? So this is how reducing agent will be helping us to get the alcohol from carbonyl compound. Aldehyde ke liye we will be taking lithium aluminium hydride, right? And ketone ke liye we will be taking sodium borohydride. Okay. Now Grignard reagent also is the one we can say way we are where we can use and get this compound, Grignard's reagent. So Grignard reagent, we have that is the formula RMGX. General formula it is. R can be taken methyl, ethyl, anything, right? Anything can be taken. X can be Br, can be I, anything can be taken. So the compound example of the Grignard reagent goes as CS3MgI. For example, if we have taken this, or if you have taken C2H5MgBr can be taken. Any example can be taken as the Grignard reagent, right? Remember, so it will be given in examination. So remember one important thing over here, formaldehyde with RMgX, what will produce 1 degree alcohol, right? It means when we treat this compound, we get the R, which is here, right, as the MgX, RCH2O, clear? And the acetaldehyde, if we take the RCHO, this with the MgX, RMgX will give 2 degree, okay? And then R C double bond O R dash ketone with the same reaction and followed by the hydrolysis, this gives the 3 degree alcohol, right? This gives the 3 degree alcohol. Are you clear? So we get the 1 degree alcohols, 2 degree alcohols by the Grignard reagent test. So formaldehyde gives 1 degree. Acetaldehyde or other aldehyde, higher aldehyde gives 2 degree. Ketone gives 3 degree alcohol, right? So flow chart thoda difficult hai making in the alcohol case, but in phenol we can draw. So let us see for phenol. Okay, we are doing the preparation. Because we can see in alcohol we have separate reactions and the properties, 1 2 3 like that categories we have. If the single product we have, we can bring from the different sides in one side. That is the flow chart called as. Look over here. Now the phenol case me, it is possible because phenol is the one single compound. Does not, we are not going to learn about any derivative. Now OH can be any side, top side, not any side, because all carbon identical in benzene ring. So the first preparation from the chlorobenzene, let us see. Chlorobenzene treated with the base alkali, I meant to say acid base reaction की तरह, we get the product at 623 K and 300 atmospheric pressure. What do you get as this process? We call it as a Dawes process. Okay, so this gives a product as sodium benzoate. Okay, and then again HCl के साथ we do the acid hydrolysis and we get as a product phenol. Clear? So this is the phenol product. Right, now let us see oleum also. This is the first. It's there in the basket, don't cry. Even oleum benzene, oleum is what? H2S2O7. This is oleum. Oleum helps to get this compound by sulfonic acid, benzene sulfonic, right? SO3H we get from here, right? This produces SO3H, so that gets substituted. Then benzene sulfonic acid ka alkali reaction and followed by the acid hydrolysis. So what do you get as the product? Phenol. Right? Next reaction, aniline. Clear? Treated with the sodium nitrite NaNO2 in the presence of hydrochloric acid. So first we get the benzene diazonium chloride and then benzene diazonium chloride heated with the water, warm water, and we get the product as phenol. This is flowchart, right? Now we can say cumene के साथ. So isopropyl, remember?
Yes.
This is isopropyl benzene. which is generally called as cumene. So from cumene oxidation O2, then this product will go for the so what I can do is to keep the similarity, I can keep hydrogen down and CH3 side. Okay. Clear? So all these mechanisms we have learned, and then again followed by the acid hydrolysis, and we get, so what comes out over here as the acetone, CH3COCH3, right now, and we get as the product phenol, right? Is this clear? All it's clear preparation. Now it is helpful in a single page you can see. So reagents are important. So once you just every morning you just see this reaction, so will be better, and you know you will get reagents are important. These are the so you can see now reagent I have shaded in a yellow color, and the violet you can see in the reactant side. Okay. So this is the flow chart for phenol preparation. Any doubt in this, Shrutia?
Yes, no, ma'am, no doubts.
No doubts, no?
And
So all your summary part, you can see your reactions in detail I have given over there. Now let's do the next ether preparation. But ether preparation very small. We have Williamson synthesis and the preparation. So we will go for properties better, na? I feel better. Properties are much. So let's begin the properties of the alcohol, and this can be learned. Excuse me. Chalo, we'll start the properties of alcohol. So here we go. Alcohol taken. The first, I will take the reagent. Alcohol has a reaction. It has a property of reacting with the sodium metal. So this is how the acidic character can be proven. And what will be produced as the product, the minus and A plus. So sodium alkoxide it is called as. What do you name this as? Sodium alkoxide. Right? And hydrogen gas will be liberated from here. Then you have second property, treating it with the carboxylic acid. And we know alcohol treated with the carboxylic, and the name of the reaction is esterification. Right? Hridaya?
yes, ma'am.
Absolutely.
The product, what you get as the ester, ROCOR dash, and water molecule will be out. Second reaction with the acyl chloride, acetyl chloride, which is, this happens in the presence of pyridine. This also follows the esterification only, but the byproduct is different. Okay, so the product goes over here the same, ROCOR dash, but since the Cl is used, so HCl will be out. You need to just bother over here this part. Next, alcohol treated with acid halide, correct? So we get the haloalkane plus water. Remember Lucas reagent test. Then it is treated with the PCl5. Okay, it gives the RCl because specifically Cl is used, so RCl, POCl3 because 5 are there, the 3 Cl over here, 4 Cl, and fifth Cl comes out in the form of HCl. Next is the PBBr3. right? So this again gives RBr. Br is taken. Reagent what you are taking, you will get that as the product. H3PO3, phosphorus. What do you call this compound as? Phosphorus acid. So we get the haloalkane में bromoalkane, ठीक है? And we get this compound. Even this can be made with the red phosphorus in the bromine. Okay. Next, thionyl chloride, SO2Cl2. What do you call this by name? Thionyl chloride. Reaction possible. It gives the haloalkane में RCl plus sulfur dioxide. Gas is out. Plus, yes, light नहीं चाहिए, date time है. No light, baby. Okay. Sorry, Hridaya, my son, he will be traveling in between. So we get the thionyl chloride over here. Hridaya, are you there in the meeting?
Yes, ma'am.
Okay. So I said, very sorry for the disturbance. He is coming in between. So here we'll treat this compound, alcohol, with the concentrated H2SO4. Next, which is as opposite, we can say, of the acid hydration we did in right first, and then now we are doing the dehydration. Correct. So when we do the dehydration with the concentrated acid and at 443 Kelvin, remember I said the temperature is important. If you take 413, ether will be prepared. So we get as the product over here alkene. ठीक है. So alcohol dehydration reaction से add this reaction, what do you call as dehydration? What do you call as dehydration? Reaction, what do you call? Dehydration. Dehydration means loss of water molecule. Clear? So this produces alkene. Now this goes alcohol even for oxidation reaction. So oxidation reaction mein what do you get as addition of oxygen happens, right? And you can have two different ways of preparation, like depending upon the alcohol, what do you take? For example, if you have taken 1 degree alcohol, right? So 1 degree alcohol will be producing aldehyde. जैसे कि how we are getting the aldehyde से 1 degree alcohol. Same way, aldehyde will be produced from 1 degree alcohol. 2 degree alcohol will give ketone. Like ketone gives the 2 degree, so 2 degree alcohol gives ketone. Are you clear?
Yes, ma'am.
Dehydrogenation reaction. Last one. Dehydrogenation में copper metal with copper we do, right? Copper over the copper metal, which is heated at 573 Kelvin. Remember, we'll pass the vapors of the 1, 2, 3 degree alcohols, and we see what happens when we do 1 degree, 2 degree, and the 3 degree alcohols. What happens? It gives aldehyde. The first one gives the aldehydes, second one gives the ketones, and this does not go the oxidation 3 degree, right? So here also the dehydrogenation may this produces alkenes. Clear? Clear?
Ma'am. Yes, ma'am.
Okay. Then phenol, last. You can hear my son is telling his spooky stories.
Yes, ma'am.
When he will be alone, he does not have any work, he will make us scare by telling spooky stories. My God. So whenever I take classes, he will try to take attention, or he will do such things. It's all just getting our attention. That's all. So let's
Yes.
see here the phenol, how it shows. The phenol has a vast property. Like we have the electrophilic substitution, all the reaction for the phenols. So thoda sa isme big flow chart will be needed. So I would take phenol in the center, and phenol, when we are taking the first, will be, you remember the bromine water ke sath reaction, right? This is bromine water said. So I'll be writing down bromine water. So bromine water ke sath reaction which happens, that gives a single product, because phenol undergo the electrophilic substitution. So where you had the negative, remember this place and this place, there the substitution happens. So Br goes at those places. So we get adds, what is the name? 2 comma, with respect to phenol, this is 2, this is 3, this is 4, this is 5, and this is 6. 2 comma 4 comma 6 tribromo phenol. Okay, then again bromine ke sath reaction, but this is not bromine water, and taken in actually carbon disulfide organic solvent. Even in this can be taken CCl4 also. So we get the two substituted product as ortho and para. OH ke respect mein Br comes to the ortho, which is a minor product, and the major product is a para derivative, OH and Br over here. So this is the major product, right? And let's see now the nitration. So first sulfonation will do concentrated sulfuric acid. Say we get the sulfonic acid. So phenol plus SO3H. It is called as sulfonic, which is minor, and the major is always para 1. So para position SO3H goes is the major product. The next is nitration. Nitration, if happens in the presence of concentrated nitric acid, right? So remember, it gives a single product in the presence of concentrated sulfuric acid as well. So it gives the single product, that is picric acid. Remember, yesterday we have done. So OH, and the places this 2, 4, 6 is the active place where the nitro go and substitute. So NO2 will be with respect to this 2, 4, and 6. So we call it as a 2, 4, 6 trinitrophenol, right? Which is called as picric acid, right? Now, when we do this with the dilute nitric acid, what will be the product? This is also nitration. This is called nitration reaction. This is also nitration. This is sulfonation, right? This is halogenation, bromination. This is also bromination, right? So dilute nitric acid ke sath, and this happens at room temperature basically. We get the two derivative again here with respect to OH. Para position and ortho position nitro groups goes. This is minor. Ortho always will be minor. Para will be the major. OH nitro over here. It's a major product. Okay, so very simple. Like if you remember the reagent, you can yourself can write like how I am writing. Without hesitation, you can go writing this compound. So now this I am writing, remember, when we do the sodium hydroxide, you have done with the all substitution, the basic reagent reaction. Now the naming reaction I am introducing here, this reaction is the Reamer-Tiemann reaction. Remember, chloroform and the alkali ke presence mein. So Reamer-Tiemann reaction, remember, I am writing here itself. What is Riemer-Tiemann reaction? Phenol goes to salicylaldehyde, right? So we get over here this aqueous NaOH we get, right? And this compound like hydrolysis, all those NaCl. So directly we can write phenol, say we can have the compound salicylaldehyde by Riemer-Tiemann reaction. Clear? Next, we can have the reaction, right? CCl4, the even the we can, as I said, we can have the product Riemer-Tiemann say he possible salicylic acid, but that is not there in the syllabus, so we need not to worry. That will leave it over here. Next is the coal-base reaction, which is given in the syllabus. So let's do that coal-base reaction. Coal-base reaction में we say we get from phenol से carboxylic acid derivative the salicylic acid. So what is the reagent taken over here? That's very important. The sodium hydroxide aqueous form, and then carbon dioxide, right? This is aqueous NaOH taken, then followed by the acid hydrolysis, right? This is coal-base reaction. So when we do this, we get the product as OH over here and COOH over here. What do you call this compound as? Salicylic acid. Got it? So coal-base reaction say we get salicylic acid, right? And Riemer-Tiemann reaction say what do you get as salicylaldehyde by phenol. Okay, so reagent we need to remember. Right, next is zinc dust reaction. Zinc dust say benzene will be formed because zinc will act as a reducing agent. So oxygen will be taken, hydrogen will be left. So no need to show the hydrogen, it will be hidden, right? Benzene is formed, zinc oxide. So phenol gives benzene by zinc dust reaction. Then sodium dichromate, this is oxidation reaction of the phenol. So it gives the pink coloration of the benzoquinone, right? Oxygen, oxygen, alternate position, double bond. So we get as the benzoquinone. Done? So phenol flow chart is very, very helpful because it has a huge property, right? Is it helpful?
Yes, ma'am.
So now let me highlight the things over here. Bromine, when we are taking the Br, okay, Br2, it is a bromine water, right? So we get the substituted product 3 position, okay? So this is the product 2,4,6 tribromophenol. But if you are taking the bromine in only aqueous, sorry, in a carbon disulfide, so we do not get the substituted product. We get the major and the minor product. What do you call this as the ortho and para derivative. Next is when you are taking the concentrated sulfuric acid and doing the sulfonation. So as usual, para is the major product. So remember always the major product. Okay, that is only asked. Next, nitric acid. Nitric acid may two things we have when we use the concentrated nitric acid. Remember, we get the highly concentrated picric acid, very, very important. 2,4,6 trinitrophenyl trinitrophenol is picric acid. The next, when you do in the presence of dilute nitric acid, same nitration reaction only, right? But we do not get the one product. We get the major and minor derivative, para derivative, and ortho derivative. This is also we call as the nitration reaction. Okay. Next is the naming reaction. It's a Riemer-Tiemann reaction. Riemer-Tiemann happens in the presence of aqueous and chloroform, followed by the hydrolysis. All such, so we get the salicylaldehyde. This is basically conversion के लिए also important. Phenol gives the salicylaldehyde by Riemer-Tiemann reaction. Second naming reaction is the coal-base reaction. Coal-base reaction के लिए reagent needed aqueous sodium hydroxide, right? And the carbon dioxide carboxylation basically, and followed by the acid hydrolysis. H plus ka matlab is acid hydrolysis. So we get as the product salicylic acid, right? Zinc dust ke sath reaction, zinc acts as the reducing agent. So we get the phenol se benzene, and zinc oxide. Next, sodium dichromate acts as the oxidizing agent, provides nascent oxygen. So we get the benzoquinone. Let me draw properly. It's not looking proper. Benzene, double covalent bond oxygen, double covalent bond oxygen, alternate position, double bond over here. So this is called benzoquinone. Clear? This is overall the properties of phenols. Then we have ethers, correct? So ethers may we have basically anisole ka property. Anisole is the most important, and that can be drawn as the flow chart, because others, if we are going electrophilic substitution, it is here and there will be the one other reaction property. So we cannot draw the flow chart for that right now. So I am looking for the questions now. Anisole ka reaction I will draw for you, and let me do the preparation also. So preparation, let me draw the ether first, right? Ethers, preparation. Preparation we are done by two ways, the Rx plus RONA. This is by the Williamson synthesis, right? Remember, it gives out the product as the ROR dash ether. Okay. Then same thing, it can be reacted with the HX. So this can be read as the properties. Look at over here how nicely it is. So if we the ether is taken and treated with the RX, that's what I told you. These are related. RX you will get, and the ROH. So I will take in this direction. I'm just enhancing the screen. Are you fine with this? Are you fine? Ether के लिए I need little bit. Let me keep here ROR dash. What do you say? This is ether, na? So we can say this name is by the Williamson synthesis. Williamson's synthesis. So we get ether. And then from other, again, this is actually preparation part we are learning. And properties may, if you look, so we can have this ether. Ether can treated with the acid halide, and what will it produce? Haloalkane and alcohol. This is the property you have learned, first property. Okay, this is the preparation you have learned as the Williamson synthesis. And then you have learned the mechanism, alcohol ka acid hydration. This is right, H2SO4 ke saath. When we do this at 413 Kelvin, then we can have a product ether, right? We can have a product as ether, right? Is it helpful?
Yes, ma'am.
This is as the first you have learned, but I am taking here as the flow chart which is helping me to draw now. So I am taking here and there a little. You can correlate two preparation for the aliphatic ether you have learned. One is the Williamson and another is the alcohol ka hydration, right? We do the dehydration basically. With dehydration, say if you just 413 ki jagah 443 if you are taking, so alkene will be produced, not ether. So temperature is very important over here. I'll highlight all the important points later. 413K, it's very important. Then over here we have actually important PCl5 ke saath reaction. So let me tell you, we get the product as over here RCl plus POCl3. Okay, and plus so we get over here as the 2RCl. So 2Cl already taken and 3. So the total we have the 5. Mama! Go from here. Okay, go. Baby. Mommy! What is disturbing Mama is in class. Mama, no, beta, please. Mommy! From Monday he will go to school, but now we are just counting days on fingers when we'll be going to school. So he's such a naughty boy. Don't let us to work peacefully. So reactions of any salt. So as this is actually aryl ether, let me example, right? Aryl ether anisole, and this is all I spoke to you about the aliphatic ethers. Now aryl ether may I would take anisole as the example and show the electrophilic substitution reaction, right?
Yes, ma'am.
Doctor, please go that room. Please go to that room. Please. Other look, I'm going to lock the door. This is not the drum part. Okay? Take it. Take it that way. Go. So how many electrophilic substitution reactions we are done? Let us recall. So go. Oopsies. Mama. So bromination, we are done ethanoic acid, and we have got the two derivative, right? Ortho and para. So OCH3 with respect to this here the PR, which is minor product, and the major is the para derivative. As the major product. So concentrated nitric acid and concentrated sulfuric acid taken here, we get not the single product, two derivatives, we get OCH3 minor, and this is next as the major product. These all are the products of the electrophilic substitution reaction, right? Now next, naming we are done. Friedel-Crafts reaction I'm going to talk now. Friedel-Crafts, right, reaction. So it depends on the alkylation and the acylation we have or not. So let's see first alkylation. Okay, so the alkylation may we will be taking the alkyl halide as the compound. So CS3Cl, and the catalyst used over here is anhydrous. This is the catalyst. Very important for 1 mark question. It's important for 1 mark MCQs specifically. Okay, so we'll do this reaction. We get the derivative again, the same two derivatives, OCH3 ortho, and this is minor. So naming is very important because here we say with respect to this methoxy will be substituent. 2-methoxy toluene it is. And the second product is the major product. With respect to this, we are having fourth place, 4-methoxy toluene. So this is the major product, right? Now next we do acylation. So acylation happens in the presence of acetyl chloride, CS3COCl, anhydrous aluminium chloride. The same catalyst will be taken over here as well. And we get as the product OCH3, COCH3. So you, with respect to the second place, 2-methoxy acetophenone. And here we get as COCH3, COCH3, 4-methoxy. With respect to this, we will go 2, 3, and 4. 4-methoxy acetophenol. Clear? This is the major product and this is the minor product. Done. Easy?
Yes, ma'am.
Right? So will it be helpful, flowchart, for you?
Yes, ma'am.
It will be helpful, right?
Yes, ma'am.
So the flow chart is started from here. Can take, and today I'm sending you notes. Can we have question and answer now? I'll be sending the questions. We'll do that.
Oh, yes, ma'am.
Good. So I have the mock paper here, mock test. Vidya, I think you have kept yourself on mute.
Yes, ma'am. I was on.
I have sent you the question, Hridaya. Just start doing it.
Oh,
These are from model papers. I'm picking up the questions which have come in the 10 years. I'm sending the question related to this chapter. Start doing it.
yes, ma'am.
I'll send this PDF as well. So will help you to know that answer.
Yes, ma'am. Yes.
Give me a minute, Hridaya.